Right, welcome back for lesson 2 in the sound topic. Last lesson, excuse me, we talked about sounds being created by vibration. And I said that this lesson we were really going to be looking at the wave, the actual sound wave itself, and how that propagates, how that moves through the air. So this is going to get a little bit technical. We'll have a look at the learning objectives first. So we are going to describe how sound actually moves through the air, or other materials as well, solids and liquids, as well as gases. And we're going to explain why they get fainter further from their source. So, you know, when you're sat talking to somebody in a room, you can hear them clearly, but if you were sat a mile away, you can't hear them at all. That sound, the volume, the intensity drops off, doesn't it? So, yeah, it won't be a long video, but it will be one that requires some attention for sure. So, how does a sound wave actually move? Well, a sound wave is something that we call a longitudinal wave. If you're doing your own research at home, if you're doing your own work at home, you may have come across transverse waves, longitudinal waves, etc. A longitudinal wave isn't something that crops up too often. Sound is probably the only example of a longitudinal wave you will look at, especially at key stage 3, maybe even at key stage 4, depending on what tier you end up sitting. But let's have a look. This is a speaker, and if you can see where I'm hovering my cursor on the speaker, a speaker to make sound moves forward and backward like this. It moves in this direction. Okay, and you can feel that. You put your hand on a speaker and it vibrates. And we talked about vibrations last lesson. This could quite easily be a guitar string. You know, I pluck a guitar string and it's going to vibrate forwards and backwards. Now, we have to sort of imagine or visualize that in front of that speaker we have lots and lots of air particles, and they are spaced out like this. Now, when that, if I go down to the bottom part now, when that speaker moves forward, it's pushing the air in front of it. So all those particles of air get compressed together. They get, they get compressed together. They get pushed together as it moves forward. You know, you can imagine that. And what we cause is this here that I'm circling with the mouse. We cause an area where these particles of gas are squashed. It's an area of high pressure, if you want to call it that. And actually, longitudinal waves are often called pressure waves because of this, because they create these areas of high pressure. So the speaker pushes forward and it pushes the air particles together to give us this here that I'm circling. But then the speaker drops back. And when it drops back, it's obviously not pushing forward anymore. It's not creating an area of high pressure anymore. It's pulling back. And that gives us this that I'm circling here. It gives us an area of low pressure. But the speaker is continually, it'll have a frequency, a number of times per second it's vibrating. It's constantly moving backwards and forwards. So it's constantly producing these areas of high pressure as it goes forward, and then as it comes back, these areas of low pressure. So we get this pattern. Now this pattern is unique to a longitudinal wave. These parts here, I'm just going to give you some extra bits that aren't really in the book. These parts here, these areas of high pressure, you may hear referred to as compression. And these parts, these areas of low pressure, you may hear referred to as a rarefaction. But don't worry about remembering those terms now. I'm just giving you those in case you're doing your own reading around the subject and you might see those words. Okay, we could quite happily just call them areas of high pressure and low pressure, but again, compressions and rarefactions are words you might see. Now, what else do we need to know about the wave? Well, if I look at the speaker is moving, or it's going to be vibrating left to right on this image. Okay, it's going to be moving left to right. The particles here are also vibrating in that left to right direction, and the sound wave itself is traveling to the right. The whole thing is happening along that whole left to right sort of axis. Nothing, what I'm trying to say here is nothing is moving up and down. Now, why am I stressing that point? Well, later on in this topic, I'm going to talk to you about transverse waves, and they don't follow the same system. They don't follow the same rule. So I really, really, really want to stress that point now, that nothing here is moving up and down. Everything is moving left to right, and that's all I'm going to say for now, and that will become more important later on. Now, this happens in the air, as you can see here. This is a gas. The same thing will happen in a solid, and the same thing will happen in a liquid. And you might be sat at home thinking, well, how can the particles of a solid... Excuse me again. How can the particles of a solid be pushed together into these areas of high pressure, into these compressions? And you'd be right to think that, because we know that particles can only vibrate. And obviously, inside a solid, this effect is far less, how can I put it? It's far less exaggerated. The areas of high pressure aren't groups of particles all really tightly clumped together. We don't have areas of low pressure where they're all really spread out. But it does happen. We do get a slight gathering and a slight spreading out. So it's not as exaggerated. Now, what does that mean for sound travelling through a solid? You might think that sound can't travel well through a solid because the particles can't move as freely as they can with a gas, but actually we get the opposite effect. You see, if I go back to this diagram, these particles that are moving left to right, as they move, they're experiencing friction. They are banging into other particles, and they are losing energy, and because they're moving quite a distance. Now, in a solid that the particles can't move as much, they are experiencing less friction. The sound loses less energy, and actually as a result of that, the sound can travel further. So in a solid or a liquid, sound travels much faster and much further than it does in a gas, because the particles in a gas, they lose a lot of energy when they are vibrating like this. Now also, you can imagine that in a gas the particles are further apart, so it can take them longer to hit into each other and produce those areas of high pressure. So let's just recap. I've added a lot of extra stuff that perhaps you didn't need to know, just in case you're doing your own reading at home. So let's recap the important things. The important things are, we call this type of wave a longitudinal wave. The speaker will move left to right, and the particles will move left to right. As the speaker pushes forward or to the right, we create these areas of high pressure, and as it drops back, we create these areas of low pressure, and that repeats. That's essentially what you need to know for your assessment. Okay, so if I've confused you with anything else I've said, fine, but like I said, just in case you're doing your own reading at home. So that is how sound travels through the air. Now you may see a diagram like this that represents sound in a different manner. Now obviously the speaker picture I've just shown you, that represents sound traveling just in one direction. But if I was stood next to this lion, it wouldn't matter whether I was stood in front of him or behind him or to the left or the right or above or below. I'd be able to hear the lion roar, because sound actually spreads out 360 degrees. It spreads out in all directions. Now it's very, 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 very difficult to draw the particles and the areas of high pressure and low pressure when we're representing the waves spreading out like that. So we tend to cop out a little bit in our diagrams, and we just draw the sound as circles coming from the source. What I want you to understand though is, if we look at the distance between this circle and this circle, so this is one sound wave, this is another, it's exactly the same as the distance between this, and it's the same between this and this. These represent the wavelength of the wave, or the distance between the compressions. Think of it that way. Okay, these represent the distance between the compressions. So if you imagine this line here as being a compression, here's the next one, here's the next one, here's the next one, and that distance will stay the same. But we know as we get further from the line, the sound is going to drop, it's going to get less loud. And we've already talked about that. We've said that the particles lose energy through friction as they travel. And that causes the intensity to drop, the volume to drop. They can no longer vibrate. Excuse me. They can no longer vibrate as well once that energy's been lost. All right. So why do sounds get quieter? Energy drops because of friction. So let's have a look at some of the keywords in the book and what we might need to pick up. If we have a look here, we're told that astronauts have to talk to each other using radio system. Why might that be? In space, why can't astronauts just talk to each other normally, relying on sound? Well, if you think about it, inside their helmet is full of air, so sound can travel through their helmet or inside their own helmet. But once you get out of the helmet, there's no air to vibrate. There's no air to create these pressure waves, these longitudinal waves. So sound just can't travel in space. It cannot pass through a vacuum. This is a key difference between light and sound. Light is actually a transverse wave, which I mentioned before. And light is capable of traveling through space, which is why it can travel from the sun to the earth, but sound can't. Some test questions I've seen has shown astronauts not being able to talk to each other in space, but when they touch the visors of their helmets together, then they can talk to each other properly using sound. And that again is because when they open the mouth, the sound wave travels through the air in the helmet, it hits the visor, causing that to vibrate. Those vibrations are passed on to the other astronaut's visor, into their helmet, and then therefore they can communicate using normal sound. So this basically says that. It says it can only travel through solid, liquid and gas. It uses the term medium for that, all right? And if you're not sure, a medium is a material something travels through. And it will be a solid, liquid or gas for the sake of sound. We've talked about the particles vibrating. We've talked about pressure waves being a pattern of high and low pressure areas. Excuse me, I'm sorry. Right, got a cold. I think we are pretty much done with that. Let's just have a quick look here to highlight what I was saying before about how well sound can travel through different medium. In the air, it travels significantly slower than through solids. And if we look at these solids, the sound is even traveling at different speeds through different solids. It's not a case that it travels at one speed in gases, one speed in liquids, one speed in solids. The type of solid or the type of liquid or even the type of gas is going to make a difference. But in air, it travels about 343 meters per second, which is a fraction of the speed of light, which is 300 million meters per second. And that's, you might get a question on your exam, why do we see the lightning before we hear the thunder? There's your example. But even at the highest speeds in a solid, it travels still the fraction at the speed of light. So we've talked today about how the waves propagate. One thing I haven't shown you is this, how you can mimic this on a slinky. You may have had your teacher demonstrate with the slinky where they have one of you hold it at one end, they hold it at the other, and they push the slinky back and forward in a repeated motion to mimic the speaker, if you like, from earlier on, to mimic the movement of that speaker. And if your teacher does that, what you'll see is a repeating pattern like this. Hopefully this is coming clear on your screen at home, but you will set up a longitudinal wave on the slinky. Try it at home if you've got a slinky of your own. Get somebody to pin it to the ground. You stretch it out and stand at the other side of the room, pin it to the ground, and then slide your hand forwards and backwards. And you'll see these areas of compression or high pressure, and you'll see these areas of rarefaction or low pressure as that longitudinal wave travels down the slinky. Right, so Miss Bladen has set some worksheets relevant for this as well. Good luck with it.